Well, it really is a great, great pleasure to be back here after 10 years and to see what you've accomplished and help you celebrate the 10th anniversary of Kavli IPMU. It's hard to believe that it's only 10 years. The IPMU is now so well established, so famous, so successful that it seems like it's been here forever. Hitoshi gave an incredible summary of the achievements of the Institute over the years. I'll have more to say about that later today, but it really is a remarkable achievement, and I congratulate you on what you've done, the incredible dynamism that one senses whenever one visits the IPMU, and your plans for the future. Quite amazing. Congratulations. Now, Hiroshi asked me to talk about the SYK model, which is a very interesting development in holographic string theory in the last year or two. And I agreed, unfortunately. I think if I had chosen, I would have given a title more like John Ellis's String Theory Today, Tomorrow, and Beyond, and given a talk of that nature. But I guess Hiroshi wanted to hear about details of ongoing work. And so I would like to warn you that this is a very technical development, rather new and complicated. And if you have any problems following it, and I'm sure many of you will, please blame Hiroshi. So what is the SYK model? The SYK model is a new rapidly developing application of what has become the central ideas in string theory for the last almost 20 years, and now sort of totally dominates much of research in the field of exploiting what seems to be a rather universal connection between quantum field theory on the one hand and string theory or quantum gravity on the other hand. This is called holography sometimes. ADS-CFT is the prime example of this. And the SYK model is one of its newest examples. SYK simply stands for three people, Sachdev and Ye, who are condensed matter physicists. Subir Sachdev is a distinguished condensed matter theorist at Harvard, who with his student Ye constructed an amusing model which exhibited the phenomena of having a quantum critical point, a phase transition in a quantum system when you vary some parameter, and yields a conformally invariant theory at the critical point. This is something that many people, especially Sachdev, believe lies behind the still not understood behavior of strange metals, and in particular high TC superconductors. Kitaev realized that this model might be a great example of holography, since it exhibits quantum chaos in a way that people believe is characteristic of black holes. And kick-started this field with lectures he gave at the KITP 2 years ago. So this is a new class of conformal field theories which are soluble in the large N limit. And they are rather unusual from the point of view of the quantum field theories that we have been using traditionally in holography, since they, in this case, have no spatial degrees of freedom at all. This is simply a quantum mechanical system consisting of a large number of Majorana fermions with random quenched interactions. Describing a system with random interactions is characteristic of disordered systems like glasses and give rise to fascinating behavior. It's rather unusual to use them in fundamental physics and especially in holography. But, as was already realized by Sachdev and Ye, these models already show signs in the quantum mechanical level of quantum gravity. They exhibit a broken diffeomorphism invariance, this time of time, in the infrared. And they, as I said, give us a soluble conformal field theory, which Kataev argued is as chaotic as it could be. Now, it's always very nice to have a soluble theory where one can work things out exactly and learn from the solubility of the theory. This theory is both soluble and maximally chaotic. Most theories are soluble because they're integrable. There are an infinite number of conservation laws or close to being integrable. In this case, we have maximum chaos and solubility, which is really unusual. And so this set of models can be used to learn about one of the most ill-understood parts of quantum mechanics, quantum field theory, chaos, and approach to equilibrium, and so on. But also, Kataev stressed that that might be a sign that this is a system which is holographic, dual to the dynamics of a black hole. In the simplest space-time imaginable, ADS2, two-dimensional space-time in a box. So I got interested in this because I love large N theories and have worked on trying to use an expansion of 1 over n, the number of degrees of freedom, to gain insight into many areas of theoretical physics. There are two kinds of familiar large N theories: vector models, in which the primary degrees of freedom are vector-like and invariant under a kind of ON symmetry, or matrix models in which the dynamical degrees of freedom are tensors, like gauge fields, which are invariant under also a UN or an ON symmetry. Vector models are kind of easy, and diagrammatically, they're easy because the only diagrams, Feynman diagrams, that survive in a perturbative treatment are bubble diagrams, which are easy to sum, give geometric series. Matrix models are much harder. Their Feynman diagrams are all planar diagrams. And the prime example of such matrix models that we've learned so much about and are very close to QCD, the standard model, are supersymmetric Yang-Mills theory in 4 dimensions. That's the CFT, which is dual to ADS in the famous ADS-CFT holography. SYK are a new class of models which are soluble for large N, in which diagrammatically one gets a whole different class of diagrams, so-called Mellon diagrams. They are somewhat more complicated than vector models and much richer, but less complicated and easier to solve than matrix models, somewhere in between. In holography, we relate a theory on the boundary, Minkowski space, to a quantum gravity theory or a string theory with an extra dimension. In the case of matrix models, the best examples, studied examples, are supersymmetric Yang-Mills theory, like the standard model, close to the standard model. In the case of vector models, the soluble vector models were very useful guides to understanding critical phenomena, phase transitions, and condensed matter physics. And what is the dual, what is the holographic dual of these conformal field theories described by SYK models? Well, for the matrix models, supersymmetric Yang-Mills theory, the bulk dual, we believe, we're sure, although it's certainly not been proven, that they are completely equivalent or dual to critical string theory and ADS times a five-dimensional sphere or some other compact space. They contain, these bulk models are principal full string theories, but in a controllable limit, they can reduce to Einstein's quantum gravity. In the case of vector models, the dual to the conformal field theories appear to be dual to a theory which is not very well understood, which contains a generalization of diffeomorphisms and invariant theories with an infinite number of higher spin fields, which are all massless. This is a very complicated theory about which little is known except the classical equations of motion. SYK is somewhere in between. It has, in the bulk, not as many degrees of freedom as a string with an exponentially rising number of degrees of freedom, but it does have a tower of massive particles, not massless, and most of the work that I've done is trying to understand what this bulk dual is. Is it some kind of string theory or some other kind of theory in the bulk which generalizes gravity? So what is the SK model? Well, it's simply a Hamiltonian. There are no fields that depend on space. There's no space, just a bunch of Majorana fermions chi. So real half of a Dirac fermion. Coupled with Q-body interactions. The I's simply are labels of an internal index. They don't label space-time spatial points. And the couplings are random. So they're chosen from some ensemble, say Gaussian, which is symmetric under rotations in this label space. And this model is attractive because it's completely soluble. And in fact, to some extent, now has been completely explicitly solved for large n in all of its details. The reason it was constructed was that for large values of the coupling or time, the dimensionless quantity is the coupling J times time. That means for large times in the infrared, it exhibits near conformal invariance. And as Kitaev showed, it's maximally chaotic. It's about as chaotic as a quantum system can possibly be. There are now believable absolute bounds on the amount of chaos on the quantum analog of the Lyapunov exponent that describes the approach to chaos. You make a small perturbation in the system, and system classically neighboring points in phase space move far rapidly apart. There's a quantum analog of that which appears to be saturated by this dynamical system, which makes it very interesting. Chaos, by definition, is hard to study. A soluble model of chaos is a great crutch. So I'll just briefly describe the simple solution, which was actually worked out was that 24 years ago. So this is our Lagrangian, a free fermion in no dimensions, just time, and with the simplest coupling of 4 fermions with random couplings. As I said, the reason that model is soluble is that when one calculates, for example, the 2-point function, there's a class of diagrams. This would be the simplest diagram that appears. This dashed line represents the correlation of these random couplings at the vertex, which after you calculate the observable, you average over. A simple class of diagrams survive. This survives if you scale j correctly as n goes to infinity, but this diagram doesn't. It falls off like 1 over n squared. And the whole series for the 2-point function can be solved by noting that the self-energy, this is the self-energy that appears in the 2-point function, is just the only diagrams that survive are these, which means that the self-energy in the function of the time difference of these points is simply the full propagator cubed. And these equations close. So these are like Schwinger-Dyson equations, but they're closed and can be solved, especially in the infrared where we drop the omega. It becomes trivial to solve these equations. Before solving them, you can see that they are invariant under time reparameterization invariance. So we have a quantum mechanical system whose solutions are invariant under arbitrary reparameterizations of time. This is the one-dimensional analog of general coordinate transformations. Now, of course, when you pick out a particular solution, you spontaneously break that invariance. In the case of this 4-body interaction, the Green's function, in the ultraviolet, where the interaction is irrelevant, is just that of a free fermion, but it acquires an anomalous dimension, the fermion of 1/4 in the infrared. And it's this infrared behavior that is characteristic of this conformal field theory that we're interested in. The invariance under time reparameterization invariance means that many things in this model are very much under control. For example, if you want to calculate the thermal Green's function, all you have to do is map the line of time onto a finite circle of radius 1 over the temperature, and then you immediately get the dependence of the fermion Green's function on the temperature. Since general ideas in holography tell you that if you put the quantum system, the quantum field theory, at a finite temperature, you create a black hole in the interior, and you can then study the physics of black holes in 1+1 dimensions. Now, what Kitaev did, and then followed up by Polchinski and Rosenhaus and Maldacena and Stanford 2 years ago, was to use this solution of the 2-point function to start solving the theory. In these large N expansions, once you have the 2-point function, in this case, everything else is a linear problem and can be explicitly calculated. For example, the 4-point function of the fermions, it becomes just a sum of ladders for large N, and has a spectrum of local operators, the singlet operators that correspond to physical observables one would believe in the bulk. And this one wants to know, of course, what these degrees of freedom represent in the gravitational bulk theory. What are their masses? What are their couplings? And their masses are simply determined by the dimensions of the operators on the boundary. They are the kernels of that, they're the eigenvalues of that kernel that constructed those iterated ladders and can be explicitly solved. So as an example of theory in which all the dimensions of the, this would be the analog of the single trace operators in ADS-CFT can be calculated very nicely and in closed form. There are an infinite number of such operators, and there's one special one which corresponds to the dominant gravitational degree of freedom. That's the one, that's O2. It would be the analog, actually, of the energy momentum tensor. Now, what these people discovered was that there's a divergence in this theory, that in this infrared limit, which corresponds to that operator of dimension 2. And that divergence is due to an explicit breaking of the diffeomorphism invariance. And this has an analog, a one-to-one analog, as it turns out, with the gravitational theory. So the theory of gravity in 2 dimensions is rather, can either be viewed as a totally trivial theory or a totally sick theory. And was, I must say, an issue of much confusion for many, many years. It was really worked out by, recently by Almeri and Polchinski, based on a slight modification of Einsteinian gravity in 2 dimensions due to Joukieff and Teitelbaum. Joukieff and Teitelbaum realized you can't really just deal with Einstein's action, since the curvature is topological. And they added another degree of freedom, which called phi here, whose equation of motion is just the constraint that the Einsteinian curvature be equal to minus the cosmological constant, equal to the cosmological constant here, minus 2. And phi has some dynamics, the simplest being just a boundary term, well, I think I got this wrong, that fixes its value to be phi naught. And what this corresponds to is the fact that in 2 dimensions, well, there's surely no gravitons. Also, the fixed curvature metric is really rigid. And the only degree of freedom left is this degree of freedom associated with phi, which has to do with, so this is a picture, Escher's picture of hyperbolic space, Euclidean ADS2. And in defining this theory, you need to specify boundary conditions at the boundary, but there's an ambiguity as to where you place the boundary. So this red curve is a circle, epsilon away from the boundary, which approaches the boundary as you take a regulator away, but you might have chosen some other curve. And the 1 degree of freedom remaining in this problem is how you approach the boundary, which is a full function of tau, tau being the parameter along this circle. The dynamics of that degree of freedom is the dynamics of pure Einsteinian gravity in ADS2, and can be shown to be exactly the dynamics of the SYK model. So from the SYK model point of view, you find from this leading operator a divergence that is only cured by keeping the first corrections to the infrared action. And you can show that that dynamics is described by the Schwarzian effective Lagrangian, which is the Schwarzian action, low energy effective action of SYK. And in the bulk, it is also the action of the dilaton, this function of tau that describes the boundary as you define the boundary conditions for Einsteinian gravity of the Joukiffe-Teitelboim modification of Einsteinian gravity. This Schwarzian action is, again, in this model, extremely simple. It can be quantized exactly. Stanford and Witten showed that this action, the path integral over this action is one loop exact. There are no corrections beyond one loop. And it is what is responsible for saturating this chaos bound. There's an absolutely fascinating story here. And given that almost proved correspondence between ADS2 quantum gravity and the SYK model, one can, and some people have already, tried to use this correspondence to study, for example, the nature of black holes. In a beautiful paper of Maldacena and try to remember, and one of his students, they showed how you can take the so-called eternal black hole, which is can be viewed as an entangled state of two black holes, and send a signal through the wormhole that connects those, the so-called Einstein-Rosen wormhole that connects those two black holes. But I certainly don't have time to talk about that, and I do want to say something about what I've been doing. So there are a whole set of generalizations of SYK. There's also another parameter Q that appears, and some very beautiful things happen when Q goes to infinity as well. There are a lot of generalizations. There are supersymmetric generalizations, either in one dimension or in two dimensions. There are higher dimensional versions of SYK in which one takes this quantum mechanical model and puts it on a different sites on a lattice in 1, 2, 3, whatever number of dimensions. One then gets chaotic models which can transmit information along the lattice as well. And it has been, condensed matter physicists have used this to study the butterfly effect. You know, butterfly flaps its wings somewhere in Tokyo, and it affects the weather in Santa Barbara. And also to discuss transport properties of materials which might describe strange metals, high temperature superconductors. There's a lot of interest from the condensed matter point of view of using such chaotic CFTs to look for interesting quantum critical points. In another development, Witten realized that these Mellon diagrams that appear in the perturbative expansion also appear in so-called tensor models in which instead of having random couplings, the Majorana fermions have many indices, so they're multi-rank tensors, in this case 3. And those tensors are coupled like this. And these are models that have been studied by mathematical physicists who are interested in constructing models of higher dimensional geometry. You know, matrix models are famous for generating diagrams that tile two-dimensional surfaces. That's one of the origins of string theory, gauge theory, string theory. The Feynman diagrams look like two-dimensional surfaces. These tensor models are constructed to give perturbative expansions that look something like higher dimensional geometries, which are much harder, if at all possible, to classify. And much work had been done on studying quantum field theories, which couple tensors in this way. And it turns out that these bubble diagrams arise as the leading diagrams in the 1 over n expansion of these tensor models. They have a very strange and unfamiliar 1 over n expansion in higher orders. It's not at all clear what set of 3D geometries they generate. But it's a totally different class of conformal field theories, which again is exactly the same as SYK in leading order 1 over n, but differs from it substantially and interesting and yet largely unexplored ways to higher orders. 1 over n, I recall, is always in these theories, on the one hand, the number of components of the quantum field theory, on the other hand, it's Newton's constant in the gravitational analog. Now, the thing I've been most interested in is what is the bulk gravity string theory. There are, in addition to this gravitational mode that dominates in the infrared, an infinite tower of massive modes, which should correspond somehow, say, to the massive modes of the string theory. And that can be directly approached by calculating. So what I've been doing with Vladimir Rosenhaus the last year and a half is to sort of solve the theory, construct all the graphs that contribute to the large n limit of the correlation function of all these singlet operators, which should determine the bulk couplings. For example, the bulk cubic couplings of the fields whose masses I showed you how they were determined, are determined if you can sum these diagrams. And since this theory is so simple, one can actually do that. The three-point functions themselves are simply numbers. Their structure is determined by conformal invariance. The numbers are not easy to calculate. Simplest example are some what are unfamiliar kinds of contact terms that occur in this theory. The cubic level, this diagram, the hard thing is to do this integral. These are points in time with full propagators represented by these lines. You have to do integrals like that, and you can, in the case of the contact term, get a rather simple and beautiful answer and take various limits, discuss its behavior. In the case of the planar, it's much harder, but we've actually managed to do these integrals, and I'll just flashing the result, which is pretty awful, but absolutely, from another point of view, absolutely beautiful. This is like the analog of this in the case of the standard supersymmetric Yang-Mills theory. We calculate the three-point function of all trace, single trace operators explicitly in terms of some hypergeometric function. F43 is not exactly a familiar hypergeometric function, but Mathematica knows how to deal with it. So what we've done after that is use these same methods in effect, in principle, not as explicit as that previous formula, to calculate all the endpoint functions in, or at least give an explicit expression. In such a conformal field theory, in a sense, once you have the three-point couplings and the dimensions of the operators, the masses, everything else is determined. What you then want to do is relate this to the bulk theory. And in particular, we can already see that the bulk theory is not a local theory of quantum fields. It can't be usefully described just as an infinite tower of bulk fields with local interactions. And we don't expect that. In the case that's most studied, ADS-CFT, supersymmetric Yang-Mills theory, we know that the bulk theory is string theory. So in this approach, what we're trying to do is, in fact, construct the tree diagrams of string theory without knowing what the string theory is. That's pretty difficult, and we're not even sure it's a string theory. One hope is that enormous simplifications for large Q, and what we're trying to do is either embed SYK in our critical string theory with some compactified dimensions. That's not unreasonable, since ADS2 is always what is the description of the physics of any theory near the horizon of a black hole. So it could very well be that, as probably in the case of the ON vector models, one can understand this as some kind of limit of critical string theory. But it might be a new kind of string theory. We really understand string theory so little, since we don't have a general principle or equations that tell us what string theory is. There might be new and totally different ways of constructing what might be called string theory or quantum gravity. Unfortunately, I don't have the answer, and I'm sure I've mostly confused you completely. So I'll end with a question mark, and thank you.